Positional encoding simply gives transformers a sense of order. Without it, a transformer sees all words at once with no clue who came first, and that breaks meaning. The fix is to add a gentle pattern to each word embedding using sine and cosine functions. Think of it like giving every word a tiny rhythm that tells the model where it sits in the sentence. That rhythm helps it understand that cat chased mouse is different from mouse chased cat. In an interview, a great answer is transformers can't track sequence on their own, so positional encoding injects order directly into the embeddings. If someone asks why sine and cosine, you can say they create smooth patterns the model can easily combine and compare. Don't worry if this feels abstract. Once you see how attention uses these patterns, it becomes intuitive. Now let's build on why transformers actually need this extra position signal. Self-attention looks at the entire sentence in one pass, which is powerful, but also means it has no built-in memory of order like an RNN. Without positional encoding, dog bit man and man bit dog would look identical because the model only sees relationships, not sequence. Positional encoding fixes that by adding a unique mathematical signature for each location, so attention can compare not just meanings, but also relative order. A strong interview way to phrase it is self-attention is position agnostic, so we inject positional information to restore mean. Real projects rely on this, from translation to summarization, because meaning changes when order changes. This part becomes clearer as you work with attention maps and see how the model uses these signals to focus on the right words. Here's the key idea behind the formula. Each position in the sequence is mapped to a pair of sine and cosine values at different frequencies, creating a unique pattern the model can recognize. Lower dimensions change slowly and higher dimensions change rapidly, so together they capture both fine and coarse position details. What matters most is that these patterns repeat smoothly and let the model learn relative distances, not just absolute positions, and they work for any sequence length without retraining. In an interview, you might say, the sinusoidal formula creates predictable patterns the model can add and compare, helping attention understand how far apart words are. A simple way to imagine it is like giving each position a musical tone. The melody changes with the sentence, and the model learns to use that melody to keep track of structure. A few follow-up questions often come up in interviews, so let's fold them in naturally. When asked why sine and cosine are used, the simplest answer is that they create smooth, periodic patterns that the model can easily combine when comparing positions. So, if someone asks about absolute versus relative encoding, you can say that classic transformers use absolute positions, while newer models explore learned or relative schemes for more flexibility. Another question is whether encodings can be learned. So, yes, many modern models learn positional embeddings directly. And if the interviewer asks about long sequences, explain that sinusoidal encodings generalize well, but learned encodings may require training adjustments for very long inputs. The takeaway is that positional encoding is the foundation that helps transformers understand structure, and every architecture builds on this idea in one form or another. Great job learning today. If this helped you feel clearer or more confident for your AI or ML interviews, tap like so more learners can find you. If you want simple guidance for every interview topic, subscribe so you never miss the next lesson. You can share your questions in the comments. I read them, and they help me choose what to teach next. And if you know someone preparing for interviews, feel free to share this with them. Keep going. You're improving with every step. I'm here to help you grow.